Okay, welcome back. Now that we've talked about infinite series, power series, we're now ready to connect power series with the estimated polynomials that we were doing in the previous section, the Taylor polynomials. So now we do that with what's called Taylor series. And this is actually going to give us a way to construct series for a lot more power series than what we were able to do so far. Remember, all the power series that we've been building so far are all based off that geometric series. So now this is going to give us more series, ways to develop more power series. So suppose f has derivatives of all orders on an interval centered around a point A. A is again the center of the series, the power series. Then the Taylor series of f centered at A is simply just taking that Taylor polynomial idea that we had and expanding it now and letting it go to infinity. Okay, so it's the kth derivative at the center divided by k factorial times x minus a to the k power. Right, and again, of course, the zeroth derivative is the function itself. 0 factorial, remember, is 1, so that would be f of a plus f prime of a, x minus a, f double prime of a over 2, x minus a squared plus, and so on, and so on, and so on. And then just like before, if a happens to be 0, then the series is a Maclaurin series. Remember, Maclaurin is just a Taylor centered at 0. So the key idea here around finding power series is to discover the pattern that the derivatives evaluated at a particular point that they follow. That's really the key idea here to come up with these Taylor series, is to look first at the Taylor polynomials and try to find a pattern for how the coefficients of the terms are coming about. And so let's take a look at an example here. So let's say we want to find the Maclaurin series. Remember, Maclaurin is just Taylor series centered at 0. So let's say we want to find the Maclaurin series for the cosine function. Okay, so we would start looking at the derivatives of the cosine function. Okay, so f of x would of course be the cosine function, and then f prime would be negative sine, f double prime would then be negative cosine, f triple prime would be positive sine, and then finally the fourth derivative with the sine function and the cosine function take us back to where we started. Fourth derivative would take us back to the cosine. Right? And then we evaluate those at our center, which for Maclaurin series would be 0. So we've done this, something similar previously. F of 0 would be 1. Sine at 0 is 0. F double prime at 0 would be minus 1. F triple prime at 0 would be 0. And so the fourth derivative, again, is just repeating that pattern, would be back to 1. And so let's start to write out our terms, the first few terms of this cosine series, and see if we can kind of come up with a pattern. Okay. So the series would be the sum as k goes from 0 to infinity of the kth derivative, evaluated at 0 in this case, over k factorial times x to the k. So of course, first term, 0 power, would just be 1. Okay. We skip the first degree power because that's got a 0 coefficient. So all the odd powers are going to have 0 coefficients. So the next one would be the second power, which would be minus 1 over 2 factorial, or just 2, but I'm going to leave it as 2 factorial to make it easier to see the pattern. Third one again would be 0. Fourth one would be back to 1, so that's going to be 1 over 4 factorial, x to the fourth. Fifth one we would skip. Sixth would be back to the minus 1 again. So it would be minus 1 over 6 factorial, x to the sixth. And then plus, skip the seventh, it'd be 1 again over 8 factorial, x to the eighth. And hopefully at this point you can start to see the pattern of what's going on here. You start to see the pattern of what's going on here. It's only going to be an even power, so we're going to have the even terms. Well, we can represent even numbers with an exponent of 2k. So, k goes from 0 to infinity, so k equals 1. 2 times 0 would be still 0. K equals 0 would be 2 times 0 would be 0. So that would be still just x to the 0, still just be 1. K equals 1, we'd have 2 times 1, which would be 2. And then the exponent would be 2, and so on. And then we also have to account for the alternating sign. Okay, so the first term was positive at 0. When k equals 1, that would be an odd power. Then k equals 2, we'd be at 4. K equals 3, we'd be back to 6. So with all that in mind, we can write our series out like this. Sum as k equals 0 to infinity of minus 1 to the k, that takes care of the alternating sign, so the even terms, 0, 2, 4, those are all your positive ones, and then the odd ones, 1, 3, so again, twice 1 would be 2, twice 3 would be 6, right? So we take care of the alternating sign that way. And then the exponents are doubled, so that'll be x to the 2k, and then that's actually over 2k factorial. And so that would be the series, the Taylor series for cosine. Okay, so that's the first thing, we found the Taylor series. And now we ask the question, when does it converge? When does it converge? So the same question we've asked previously about power series, except now we know specifically what power series we're talking about. We're talking about the power series, or the Taylor series, for cosine. Okay, so we ask the question, when does it converge? Well, since we're dealing with factorials, the ratio test is probably our best bet. Ratio test. So remember the way the ratio test works, we're going to be taking the absolute value of ak plus 1 over the absolute value of ak. So plugging that in, k plus 1, absolute value, so we're going to drop the alternating sign thing, that doesn't matter, because we're looking at absolute convergence. So for k plus 1, we'd have absolute value of x to the 2 times k plus 1 divided by k plus 1 factorial. And then that's going to be divided by the absolute value of x to the 2k. And I'll fix the denominator error. I made a mistake. I'll fix that in a moment. And that's going to be over the 2k factorial. So this actually should be 2 times k plus 1 factorial. Okay. And then close my other absolute value bar over here. And then we just got to clean this up. So remember, when we divide stuff, that we multiply by its reciprocal. So I'm just going to put all this together in one big absolute value. So I'm going to have x to the 2k plus 2 on top, and I'm going to have 2k plus 2 factorial, and then that's going to be times 2k factorial on top over x to the 2k. Now remember that 2k, that factorials, are always that factorial down to 1. So we can take that 2k plus 2, and I can write that as 2k plus 2 times 2k plus 1 times 2k factorial. Right. That way, the 2k factorial will cancel out of both pieces. We also have a 2k, which will cancel out with the x to the 2k, so that in the end, we have the following expression. We have just an x squared left on top. That'll be inside absolute value. K's, we don't need anything. That'll just be 2k plus 2, 2k plus 1. All right, and then we take the limit of this thing as k goes to infinity. And of course, x squared is just a constant, so we fix that no matter what value it is. It's going to be some constant. So the denominator goes to infinity. The numerator is some fixed constant. So this whole thing goes to 0. All right, so this whole limit goes to 0. And 0 is always less than 1, no matter what x is. And so therefore, this thing converges no matter what x is. So it converges on the whole real line. So for all real numbers, this thing converges everywhere. And now there's another result later on that lets us finally say confidently that it actually converges to cosine x everywhere. And so we can say now that the cosine of x is equal to the infinite series. K goes from 0 to infinity. K goes from 0 to infinity of minus 1 to the k, x to the 2k, all over 2k factorial. Okay, for all real numbers. The infinite series converges for all real numbers. Okay, so we have this result now, our first Taylor series. Like I said, there is another result that says that when a power series converges, when a Taylor series converges, it will converge to the function it was used to build it. And so there we have our result.